So this will be the first lecture over chapter 20. So this chapter is over carboxylic acids. So this first lecture we'll look at how to name carboxylic acids, look at their physical properties and some other fundamental properties of carboxylic acids. Okay, so first how to name them. So if we name these carboxylic acids, so 1, 2, 3, 4 carbon chain, so that would be butane. So to name it as a carboxylic acid, we just change the E ending to oic acid, so that would be butanoic acid. So carboxylic acids have to be at carbon number 1 because of the OH has to be at the end of the molecule. So you don't have to say butan 1-oic acid because it's understood that it's at carbon number 1. And so in this case, this molecule 1, 2, 3, 4, 5, so 5 carbon chain. And so even though that's a 6 carbon chain ring, the carboxylic acid has higher priority, so it has to be part of the parent. So the cyclohexane would be a substituent in this case, so that would be a 5-cyclohexyl, and then pentane would become pentanoic acid. So pentanoic acid. Okay, so a little bit more complex for this next one. So 1, 2, 3, 4, 5, 6. So OH doesn't have priority, you call it hydroxy. So again, 6 carbons, so that would be hexane. To take care of the carbon-carbon double bond, you change that A to E. And to take care of the carboxylic acid, you change the E to oic acid. So this would be a 5-hydroxy, and then hex, and the carbon-carbon double bond starts at carbon number 2, so put the 2 right before the E, so 2N, and then oic acid. So that is a chiral carbon at number 5, but the stereochemistry is not shown because I have not drawn it in 3 dimensions. Right, to show the stereochemistry, you would need to have it drawn on solid or dashed wedges so that you knew where everything was at in 3D. So you don't have to worry about R and S, even though that's a chiral carbon, because I have not illustrated to you if it's R or if it's S. In fact, when it's drawn like that without the stereochemistry clearly defined there, that would imply that it's racemic, that it's an R and S mixture. Okay, for this next one, 1, 2, 3, 4 carbon chain. So when an amine doesn't have priority, if you remember, you call it amino. So this would be 3-methyl. Well, let's put them in alphabetical order, right? So 2-amino, 3-methyl, 4 carbons, butanoic acid. Although in this case, this would be more commonly referred to by its common name, because this is an amino, that's a carboxylic acid. Whoops. All right, so you have a carboxylic acid here, and you have an amine here, so that's an amino acid. So you don't have to know the trivial name here, but this would be more commonly called valine, which is one of the 20 common amino acids. So that's one feature of amino acids, is the 20 naturally occurring ones have an amino group on carbon number 2, and then what's different is what's called the side chain, what the alkyl group that's on carbon number 2. Okay, so many carboxylic acids do have a common name associated with them. So this one with 1 carbon, so the technical name would be methanoic acid, since it's 1 carbon, but nobody calls it methanoic acid. It's more commonly called formic acid. And so if you remember, this aldehyde with 1 carbon is called formaldehyde. Technically it's methanal, right? Because you name aldehydes with the AL ending and it's 1 carbon, but nobody calls it methanal, they just call it formaldehyde. So again, that 1 carbon unit has this prefix form. So formaldehyde, formic acid. So same here with the 2 carbon chain, 1 2 carbon chain. If you remember, this aldehyde is technically ethanol, but nobody calls it that. Most people just call it acetaldehyde, where this 2 carbon chain is given as prefix acete. So same here, 2 carbons, technically that would be ethanoic acid. So that would be the IUPAC way of naming it, but it's more commonly just called acetic acid. So that would be the carboxylic acid that you find in vinegar, for example. Okay, so this next one again is a common name, benzene with 1 carboxylic acid attached to it. That would be benzoic acid. So this would be a 3 amino benzoic acid, or meta-amino or M-amino. Okay, so this next one, 3 carbon chains, so this would be 2 hydroxy. 3 carbons is propane, so that would be propanoic acid, but this one has a common name as well. All right, that carboxylic acid is called lactic acid. So that would be something that can, if you're exercising strenuously, that can build up in your muscles and cause muscle soreness. Okay, so many carboxylic acids are diacids. So how do you name a diacid? So 1, 2, 3, 4, 5. So that would be pentane. And to name it as a carboxylic acid, you keep the E to make it easier to say. So it'd be pentane and then simply dioic, if I could spell. There we go. So it'd be pentane dioic acid. So with a fluorine on carbon number 2, so this would be 2-fluoryl. Pentane. Again, so we're keeping the E to make this easier to say. So pentane dioic acid. Yes, so again, we would not need to specify that it's at carbon 1 and 5 because there had to be at the ends of the molecule, and we're going to number the carbon chain to keep the carboxylic acids in the parent. Okay, so the next one, so that would be a cyclohexane. So disubstituted, so then you have to worry about is it cis or trans. Well, this carboxylic acid's on top of hydrogen. This carboxylic acid's on bottom of hydrogen, so they're trans to each other. So this would be trans. And in cyclohexane. And in this case, you would need the numbering scheme because the 2 carboxylic acids could be 1,2, 1,3, or 1,4 with respect to each other. So here they're 1,2, cyclohexane, 1,2. Man, I cannot spell. So that will be trans cyclohexane 1,2 dioic acid. Okay, so this is a carboxylic acid. And if you remove the proton from it, so this would be its conjugate base. Because as we'll see, that hydrogen is very acidic. And so if you take off the hydrogen from a carboxylic acid, then you make what's called a carbox, or carboxylate. Okay, so their basic structure, so because of the C double bond O, so that carbon's sp2 hybridized, right? So these bond angles are about 120 degrees. And it is resonance stabilized. So you do have that resonance form for carboxylic acids. Obviously, it looked more like the one on the left than the resonance form on the right. So in terms of boiling point, so if we compare the alkene, the ketone, the alcohol, and the carboxylic acid, so you can see their boiling points, they all have about the same surface area. So the difference in boiling points, well, we know the ketone has a higher boiling point than the alkene because it has a dipole, so it has dipole-dipole attractions. Right, where the partial negative oxygen would be attracted to the partial positive carbon. whereas the alcohol can form hydrogen bonds, and so that's going to increase its boiling point relative to the ketone. And the carboxylic acid is even more polar. It forms hydrogen bonds as well, but it will typically form dimers, and those dimers are very strong hydrogen bonds, and that gives it an even higher boiling point higher boiling point than alcohols have. And so obviously if you just start increasing the carbon chain on the carboxylic acid, then you have more surface area, so now that's going to increase the boiling point as well. Okay, so in terms of water solubility, so the formic acid, acetic acid, propanoic acid, and butanoic acid are all infinitely soluble in water, meaning they're miscible in water in all proportions. And then if you just go to one more carbon, 5 carbons, now the water solubility falls off dramatically. Only 3.7 grams of that dissolves in water, in 100 mils of water. So if we compare that to the alcohol, so the 4 carbon alcohol is not miscible in water. Only 7.3 grams dissolves in 100 mils of water. So the carboxylic acid of the same carbon length is more water soluble than the alcohol. Right? Why would this be? Well, the carboxylic acid is more polar, right? It's got more places that it can hydrogen bond to water. So the carbonyl oxygen can hydrogen bond to water, as can the OH. So it can more extensively hydrogen bond to water. It's more extensively solvated, so it's going to be more water soluble. Right, you see that with the 5 carbon chain as well. Right, with 3.7 grams dissolves in 100 mils of water, but for the alcohol 5 carbon chain, only 2.2 grams dissolves in 100 grams of water. So the most fundamental property of carboxylic acids is that they are acids. So if we compare a carboxylic acid to an alcohol, so if you put them in water, then they can ionize. So basically a water molecule can take off the hydrogen and to make the carboxylate, and H3O+, or similarly for an alcohol, a water molecule could take off the hydrogen from the OH to make an alkoxide and H3O+. But if we look at the pKa value, so the carboxylic acid has a pKa of about 4 to 5, whereas an alcohol is about 16. So there's a difference in pKa values of about 10 to the 11th. So that's carboxylic acids are significantly more acidic than alcohols. So why are they so much more acidic than alcohols? Because the conjugate base carboxylate is a lot more stable than the alkoxide is. So if it's more stable, then it's easier to form. So why is the carboxylate so much more stable? Well, so this negative charge on oxygen, you can draw a resonance structure, right? You can delocalize the negative charge into the carbon-oxygen double bond. So that negative charge is shared 50-50 by 2 oxygen atoms. And again, anytime that you can delocalize charge, if you can delocalize the electrons, that will stabilize the electrons. Whereas if the alkoxide, the negative charge on oxygen is 100% localized on that oxygen, so that's going to make it less stable, that's going to make it harder to form. Okay, so let's look at several factors that affect the acidity of a carboxylic acid. So if we compare acetic acid to trifluoroacetic acid, and if we look at their pKa values, the trifluoroacetic acid is significantly more acidic, right? About 10 to the 5th times more acidic. So why is that? So if it loses a hydrogen to form the carboxylate, and you have a negative charge on oxygen, so again, anytime you can stabilize that negative or delocalize that negative, it will stabilize it. So they both have the same resonance form, where you can delocalize the electrons through the carbon-oxygen double bond. right? But what do the fluorines do? Well, so what do you know about fluorines? Is that they're extremely electronegative, right? It's the most electronegative atom in the periodic table. So they're going to be pulling electron density through the sigma bonds. That's what's called induction. So they'll be pulling electron density towards themselves and delocalizing some of that electron density onto themselves. And so that's going to help stabilize the carboxylate, make it easier to form. So the trifluoroacetic acid is much more acidic. So in general, anytime you have electron withdrawing groups near the carboxylic acid, that's going to increase the acidity of the carboxylic acid because it's going to provide stabilization of the negative charge on the conjugate base through induction. Okay, so we can see that here if we compare these three carboxylic acids where you have a fluorine versus a chlorine versus a bromine, and obviously fluorine is more electronegative, so fluorine would do a better job of stabilizing the negative charge of the carboxylate, and you can see that reflected in the acidity, right? If you remember, as pKa goes down, right, acidity goes up. So fluoroacetic acid is more acidic than chloroacetic acid, which is more acidic than bromoacetic acid. And then obviously the more electron withdrawing groups you have, 1 versus 2 versus 3, that's going to help stabilize the negative charge on the carboxylate as well, which is going to make the acid more acidic. So you can see that the trichloroacetic acid is much more acidic than the dichloroacetic acid, which is more acidic than the chloroacetic acid. Okay, so the number of electronegative groups by the carboxylate, the more of them are, the more acidic it's going to be, and also the more electronegative that atom is, the more acidic it's going to be. And then as these next examples show, the closer those electronegative groups are to the carboxylic acid, the more of an impact they would have. So you can see if the chlorine's on the second carbon, it's more acidic than if it's on the third carbon of butanoic acid or the fourth carbon of butanoic acid, which if we compare butanoic acid to 4-chlorobutanoic acid, there's not a big difference in acidity. So, and there's a big difference here, right, between the 2-chloro and the 3-chloro. So the effect of the electron withdrawing group falls off dramatically as it is further away from the carboxylic acid. So the closer something is to a carboxylic acid that's electron withdrawing, the more of an impact it's going to have on its acidity. So all of this same logic applies to benzoic acids. So if we compare trifluoro methyl benzoic acid to toluene, to the CH3 there, so this is an electron withdrawing group, right? The fluorines are going to draw electron density out of the benzene ring, so that would stabilize. If you put a negative here, that would stabilize a negative charge there, so it makes this proton easier to remove. Whereas the methyl groups are electron donating, and so if you had a negative here on a carboxylate, that would destabilize that negative charge, making it harder to form, so the carboxylic acid would be less acidic. Okay, so we see that here too. If you remember, nitro groups are electron withdrawing, and OR groups are electron donating. So again, the nitro group can remove, in this case, the electrons from the benzene ring by resonance. So if we consider the conjugate base, so you could put a positive charge near that carboxylate, so that's going to help stabilize the negative charge. Whereas the methoxy group is electron donating, so you could put a negative charge, so then if we lose the proton and consider that resonance form, so if we put a negative there, then that would destabilize the negative on the carboxylate, so that would make it harder to form, so the acid is less acidic. Okay, so since carboxylic acids are acids, if you react them with bases, then they're just going to do an acid-base reaction. So if you had hydroxide as a strong enough base to totally deprotonate a carboxylic acid, so that reaction lies 100% yield to the carboxylate form. Right, hydroxide is not a strong enough base to deprotonate an alcohol totally, but it is a strong enough base to totally deprotonate a carboxylic acid. Bicarbonate. Right, if you remember that polyatomic ion from general chemistry, so sodium bicarbonate, baking soda, is a strong enough base to deprotonate a carboxylic acid as well. So you can take a lone pair of electrons on bicarbonate, bond to that hydrogen, and those electrons become a lone pair to make the sodium salt of the carboxylic acid. And then you would make you'd make carbonic acid as a side product, and carbonic acid can decompose to make CO2. So OH and H can make water, and then you can make CO2, which is a gas. So this would be one way that can be used to detect the presence of a carboxylic acid. If you think something's a carboxylic acid, add some bicarbonate to it. If you see gas bubbles forming, probably it was a carboxylic acid that got deprotonated to make the carboxylate, and then carbonic acid, which decomposed to make CO2 and water. Okay, so you can use the fact that carboxylic acids are acidic. You can use their acidic properties to for usefulness in lab. If you want it, you can change something's solubility properties, for example. So if you take benzoic acid, which is basically not soluble in water, only 0.3 grams dissolves in 100 grams of water, and you react that with sodium hydroxide to deprotonate it to make the sodium salt of benzoic acid. That's an ionic compound. It's much more polar, and this is water soluble. So how could you use that in lab? Let's say you had a mixture of benzoic acid and cyclohexanone, and you wanted to separate them. Well, you can manipulate their solubility properties in order to do that. So if you took these and dissolved them in ether, diethyl ether, and then you added some 1 molar aqueous sodium hydroxide to the separatory funnel, then now you have 2 layers because ether and water don't mix, but the cyclohexanone will stay dissolved in the ether layer, and the carboxylic acid will react with the hydroxide, right, to make the sodium salt, which is now aqueous, water soluble. So it'll be in the aqueous layer. So now you've got the 2 compounds separated in the separatory funnel. So now you would drain the aqueous layer out the bottom, and then you would leave the ether layer containing the cyclohexanone in the separatory funnel. So now you physically have them separated, right? So what you would do then is you would pour the ether layer out the top into a round bottom flask, for example. You know, why out the top and not the bottom? Because if you drain it out the bottom, there may be some trace aqueous layer there that would contaminate it. So you pour it out the top and then evaporate the ether off, and now you've got the pure cyclohexanone. And in terms of the carboxylic acid, it's now in the sodium salt form. If you wanted to get the carboxylic acid back, you have to neutralize it. So if you add HCl, then O- pick up a proton, and now you have the carboxylic acid, which is not water soluble. So if it's a solid, it precipitates out, and then you just filter it off. Right, so you set up like a Buchner funnel with some filter paper on it, filter off the precipitate carboxylic acid, and dry it, and now you've got your carboxylic acid separated and pure as well. So all you did is manipulate the solubility properties by making its conjugate base, made it aqueous, made it water soluble, and then once you separate it, neutralize the pH, carboxylic acid precipitates out, so you filter it off. Okay, so you can also utilize this to make soaps and detergents. So if we took this, what's called a long chain fatty acid, because of the very long hydrocarbon chain. So if you react that, so obviously this is not water soluble. I think this is about 19 or 20 carbons. So if you react that with hydroxide to make the sodium salt. Well, that part is now hydrophilic, but you have a whole lot of the molecule that is hydrophobic. And so this little bit of hydrophilic portion is not enough to make that molecule water soluble. But what it will do is it'll form compounds like this, or what's called a micelle, which has a hydrophobic interior, because all of the hydrocarbon chains, which don't like water, will go to the interior. So it'll form a sphere, basically, with all of the hydrocarbon chains on the inside of the sphere and all of the carboxylates on the outside of the sphere. Right? Because if the carboxylates are on the outside of the sphere, then they can interact with water, right? They're hydrophilic, so they'll make hydrogen bonds to water. So all of the carboxylates will be hydrogen bonded to water. If you remember from Gen Chem 1, when we talked about ion dipole attractions, the sodium cations will interact with the oxygens of water, so they'll be solvated. And then all of the hydrocarbon chains, they will interact with each other. So you have a hydrophobic interior. So this can be useful because something like grease, which is very nonpolar, would go into the interior of that micelle, and then you wash it away, and so now you've cleaned something, right? So these long-chain carboxylic acids, once converted to their salt form, then they can be used as soaps and detergents. Okay, we'll stop there.